This PowerPoint describes the relationship between Gibbs free energy, delta G, and equilibrium, particularly the equilibrium constant. What have we learned so far about the equilibrium constant K? Well, most importantly, perhaps, is it tells us where the equilibrium position is for a reaction. So if we have a reversible reaction, A goes to B. The magnitude of K tells us whether products are favored or reactants are favored. So if we have a large K, let's say greater than 1, that means that products are favored. If we have a small k, let's say less than 1, that means that reactants, or the denominator, is larger. It's also important to remind ourselves that if we have a large K in the forward direction, so let's say 10,000, that in the reverse direction, that's if we reverse a reaction, it's 1 over K. The K in the reverse direction, the K would be small. Okay, so that's kind of intuitive, I think. All right, so delta G also tells us how much products may or may not be favored in a reaction. So remember that if delta G is negative, that is a spontaneous reaction, and any spontaneous reaction favors product. And the more negative it is, the more products are favored. I'm not sure if any of you remember this or might be able to kind of figure it out, but what is delta G? What is the free energy change of a reaction that has reached equilibrium? Look at the possible answers and see if you have a gut feeling or if you know. It turns out that delta G is 0 at equilibrium. And that kind of makes sense. Well, it makes very much sense, right? Because you think of delta G as the driving force. And if you're at equilibrium, the system has reached the lowest possible energy point, and there's no driving force to leave that lowest energy point. Let's look at a couple of free energy graphs. So notice on the y-axis it's not delta G, it's not change in free energy, it's just free energy. And the x-axis is the extent of reaction. And so the graph on the left represents an exothermic or exergonic reaction. I should have written exergonic since it's in terms of G. And delta G is negative. On the right, we have an endergonic reaction where delta G is greater than 0. Now look at the difference in the two graphs. Probably the most important thing, remember what delta G is, that it's the difference in energy between the reactants and the products. And the products, which is on the far right, have a lower energy than the reactants. What type of reaction is that? When the products are at a lower energy, that means all of this extra energy has to be released into the surroundings. So that's why it's exergonic. So when we are talking about delta G instead of just enthalpy, delta H, usually, since that's total energy, we say exergonic instead of exothermic. So that's one key piece of information you can get out. If you're asked to identify where equilibrium is, you want to pick the lowest energy, right? That's always equilibrium. That's why it stops there. And notice that delta G is the slope in this, right? So if you're at the equilibrium point, the slope is 0, right? Delta G is 0 down there. All right, so let's look at the difference between the two graphs. So first of all, if you have an endergonic reaction, one that requires input of energy to occur, so notice now that the products are of higher energy. So delta G is positive for this type of reaction. The equilibrium point is still the lowest point on the graph. However, a key difference here is where the equilibrium position is. Notice in the endergonic reaction that the equilibrium position is closer to reactants. What does that mean? Well, if a reaction is endergonic, okay, so if delta G is greater than 0, if it's a positive, then that means reactants are favored. So that means the equilibrium is going to be reached when you have more reactant than you do product. On the other hand, and this is an important concept, so if this is kind of too much the first time through, just tag it, go back and make sure you understand it, okay? So for an exergonic reaction, a reaction where delta G is less than 0, that means it's a spontaneous reaction, right? And it also means that products are favored. And so when you reach equilibrium, you're going to be closer to products or have more products in the mixture than you will reactants. All right, so here's just kind of a little brain puzzle. See if you can figure it out. If you have a simple reaction and K is 1, and you start with an initial concentration of A, that's the reactant, at 1 molar, what are going to be the concentrations of A and B at equilibrium? So if you've already figured it out, you're faster than me, but I'm going to give you a little hint. Remember what K is. It's products over reactants. See if that helps you. I'm pausing just to give you a chance to think. So, I like this question. If you're starting at 1 molar A, and at the end, you know that the concentration ratio of B to A has to be 1, right? Because they say K is 1. And you start at 1 molar, the only combination of reactant and product that can give you a ratio of 1 is if the concentration of A equals the concentration of B, right? And the only way to do that, if you have 1 molar solution, is if both of them are 0.5 molar. Talking a bit more about that situation, same thing, reaction A going to B, starting with 1 molar, and K equals 1. As the reaction first begins, so if we begin with concentration of A at 1 molar and no B to begin with, what will be the sign of G? That what I'm getting ready to say is a very simple concept that students forget, and I want you to make a note of it. It's really important. And that is anytime a reaction happens, delta G under those the situations that are present, is negative. So anytime something happens, delta G is negative. Otherwise, it wouldn't happen. So this reaction is happening, okay, in the beginning situation where you have concentration of A of 1.0 and no B. So in the beginning, what is the initial sign of delta G? It's negative simply because it happens. Now, if the reaction moves beyond the equilibrium, okay, so remember equilibrium is when the concentrations of each of them are equal. And so if it moves beyond that, so now instead of 0.5 of each of them, that means we would have less of A, right, and more of B. So if it did move, what would the reaction of G be? In that case, remember equilibrium is the lowest possible energy. So if it moved beyond equilibrium, delta G would be positive. So let's sketch the graph. So if you have free energy in the y-axis and you have the reaction progress on the x, that type of graph always looks like this. Here's equilibrium. So reactants are over on the left side, products are on the right side. So when you first start the reaction, the change in G is negative, less than 0, because you're going downhill, you're giving off energy. But once you're at the equilibrium, if you try to go towards product, delta G is going to be positive, unfavorable. Be able to interpret the graphs I've been showing you for free energy versus reaction progress. I've shown 3 or 4 of them already, so make sure that you can sketch one, that you can interpret, and that you can label all the key points on one. These are just other stuff. Here's a very simple type question using a free energy curve. Look at the graph here, and for whatever reaction this might be, what's favored in this reaction? Are products favored or are reactants favored? And how can you tell? Well, you look for the equilibrium, you look for the low point in the graph, and if the low point is closer to products, then it's product favored. And if it's product favored, what can you say about K? That means that in that case, K is greater than 1. Products are larger than reactants. So at this point, I might be beating a dead horse, but obviously this concept is important. So anytime you're going in a direction where free energy is decreasing or negative, it is going to be spontaneous. So, I mean, if you started at the product and had no reactant, if you were going in the reverse direction, it would be spontaneous to begin with, right? When you reach the lowest point, remember that's equilibrium and delta G equals 0. There's no driving force to do anything. And again, if you were to go from equilibrium back to reactant, that would also be non-spontaneous. Delta G would be positive. So back to the title of the entire PowerPoint, what is the relationship between equilibrium constant and change in free energy? Here is the mathematical relationship, but we could also summarize it conceptually. We could say for a spontaneous reaction, delta G is less than 0, it's negative, and we also know that K is greater than 1, or that products are favored. If a reaction is non-spontaneous, delta G would be greater than 0. That means it would be positive, and it would mean that it's reactant favored. And what does that mean about K? That would mean that the reactants, which are in the denominator, are larger. So that means K would be less than 1 for a non-spontaneous. But here's a mathematical relationship. You can actually calculate one from the other. And again, if you just look at it mathematically, if delta G is negative, that means that if you do the math, K is going to be greater than 1. If delta G is positive, because of this negative sign here, that means that K is going to be less than 1. So that's important relationships to remember too. Just to kind of cement that relationship in, look at these values. So if you have a very, very small K, so that means this reaction does not want to happen at all. And that's backed up by the value of delta G, which is very positive. It's a large positive. So in this case, reactants are favored strongly. It doesn't want to go toward product at all. Look at the other end of the spectrum. Now you have a very, very large K, very, very large K, which means products are extremely favored, which is supported by the fact that delta G is very negative. One of the things I want to clear up in this lecture is that let's look at two delta G's that are both negative. So let's look at one that's maybe negative 10 kilojoules, and let's compare that to another one that's maybe minus 100 kilojoules. I noticed a unit or two ago that some of you were saying, well, if delta G is negative, it's spontaneous, and one spontaneous reaction is the same as another. That is not true, okay? So, well, that's not going to work. Oh, okay. The more negative delta G, the more spontaneous, which is simply another way of saying more products. A larger percent of products will be formed. All right, so the more negative delta G is, the more product favor it is, and the closer the equilibrium will be to the product side. If K is about 1, most people say if K is between 0.1 and 10, that the equilibrium position is going to be roughly equal between products and reactants. And of course, if the equilibrium point lies closer to reactant, that means that delta G would be positive. All right, so it's kind of repeating the same thing over and over in different ways. Now, you've probably noticed in a lot of these thermodynamic properties, we use what's called a naught sign. And just to remind you what that means standard conditions. And so anytime you have a table of values that you're referring to help you work a problem out, anything that's in a published table is going to be the standard conditions, okay? And that's so that you can compare one reaction to another reaction under the same set of conditions and see how the values change. However, in real life, standard conditions aren't often used. Okay, so standard conditions would be room temperature, which is around 25 degrees Celsius or 298 K, and initial concentrations of reactants of 1 molar. There is also a related equation that allows you to calculate the free energy change for a reaction under non-standard conditions, which is the vast majority by far. And so basically, the value of delta G under non-standard conditions is typically quite close to the delta G under standard conditions. So you can kind of think of the RT log Q as a correction factor for the non-standard conditions. So remember what Q is. Q is called reaction quotient, but it's the same formula as K. So that's products, right, over reactants. But the difference being that Q, to calculate Q, it's any point in the reaction. It doesn't have to be at equilibrium. And remember, where Q comes in very handy is it tells us which way a system or reaction will shift in order to get to equilibrium. So if Q is less than K, that means that there's not enough product at the current time. And so which way will it shift to reach equilibrium? If there's not enough product and you need more product, it's going to shift right to reach equilibrium. If Q is greater than K, that means there's too much product, right? Means the numerator is too large. If there's too much product, it's going to shift away from product toward reactant, which is a shift left. So that's just kind of a reminder of what Q is telling us. Again, going back to our free energy graph and remembering that at the lowest point, you're at equilibrium. So if you calculate Q and Q is less than K, remember that means you don't have enough product. That means it will be spontaneous in the direction toward product until equilibrium is reached. On the other hand, if you calculate that Q is greater than K, that means you have a situation which is too much product, and so the reaction will shift left back towards reactant. And when it does shift left, it is spontaneous until it reaches equilibrium. The bottom line is if you're not at equilibrium, the reaction will be spontaneous until it reaches equilibrium. Regardless of whether it is on the left or on the right, it will be spontaneous as long as it's moving towards equilibrium. Let's use this equation for standard conditions and just kind of get comfortable with using it. So R is the gas constant, and again, anytime you are talking in terms of energy, you want to use the R value that is expressed in terms of energy. Temperature should be in Kelvin. Alrighty, so this is calculate K at 298. Okay, it's standard conditions, so that's why we're using, and also the fact that they say K tells you it's equilibrium, so you're using the simplified form. And you need to be able to rearrange this equation to solve for K. Now, if the problem asked you for delta G, you'd be all set. How do you rearrange this to solve for K? Well, the first thing you want to do is divide both sides by RT. So I'm going to move the negative sign over too. So I'd get negative delta G divided by RT equals natural log of K. Now, do you remember how to get rid of natural log? You use the factor of E. So both sides now become an exponent for E. And when you have E and natural log together, they disappear. So what I end up with now is that equilibrium constant equals E raised to the minus delta G over RT. So if a problem asks you to solve for equilibrium constant, this is the form of that equation you want to use. So showing the actual math here, and I want to point, so listen carefully to what I'm getting ready to say. Since this whole expression that you're plugging in numbers is an exponent, that means any tiny little change is going to make a huge change in the value of K. So do not round, don't do any truncating or rounding for this value. Just leave it in your calculator as can be. So in other words, you don't even want 141.6, don't even round that to 142. Don't round anything here because then it's going to make a huge difference. You could prove that to yourself. Plug in your calculator the difference between E raised to the 57 and E raised to the 57.2. It's quite substantial, and if it's a multiple choice question, it's going to throw you off. So go ahead and try to enter all this, just kind of give yourself practice. And I want to point a couple other things to be careful of. You might wonder, what the heck is this? What are we doing? So the minus 141.6 kilojoules per mole was given to us in the problem. So if you go back to the problem, that was given to us as free energy change. I want to point out to you that it is a negative value. So you always want to look at that. It means it's spontaneous. So if it's spontaneous, what type of value do you expect for K? You expect a very large value for K because that's the value of K you get for a spontaneous reaction. So you need a positive exponent on K. It needs to be a large value, and it is. So just so you don't make a miscalculation. But back up here. Notice that R, 8.314, is in units of joules, and the given delta G is in units of kilojoules. So unless a problem mentions specifically, it doesn't matter whether you work in joules or kilojoules, but the units have to match each other. So all that's going on here is they are converting the given kilojoules units to joules so that they match the joules unit in the R value. Almost done here. Just another part B to the problem. So we're going to move to non-standard conditions, okay? We're still at 25 degrees C, but since they gave us concentrations, and just to remind you, we haven't worked much with pressure, but K can be in terms of pressure or concentrations. So if it's in terms of pressure, same thing. You just put the pressure, you treat pressure like concentration, they're directly related. Same thing, okay? Pressure products over pressure reactants, again with some, if there's a coefficient in the balanced reaction, that becomes an exponent. So now, since it's non-standard conditions, because it's not, standard conditions would be 1 atmosphere. And so we have to use the other equation for delta G. So delta G under non-standard conditions equals delta G standard conditions plus RT log of Q. And so we've got to figure out what Q is before we can do anything else. So Q, remember, is products over reactants. In this case, it's in terms of pressure. So look back at the reaction. So it's going to be the pressure of SO3, that's the product, and SO3 has a coefficient of 2, so that pressure is going to be squared, divided by the pressure of each of the reactants. Now, if there were any reactant or product that was not a gas, you leave it out of the pressure equation. You just literally leave it out of the entire expression for Q, and that's fine. So in the denominator, the reactants, we would get the pressure of SO2 squared, because there's a coefficient of 2, times the pressure of oxygen. And then you just plug in the values of pressure that you were given. So let's look what that would be. Plugging everything in, and again, as you might imagine, the most common error here is forgetting these exponents, so that's why I always want you to write the generic expression for Q or K first. So when you plug in all these values, you are going to get that Q is 4. So go back and look at the value for K. You always want to compare Q to K. K was given in the problem, and it's huge, okay? Very product favored. So what do we have here? We have that Q is less than K. What does that mean? That means there's not nearly enough product, right? There should be almost all product. And so which way will it shift to reach equilibrium? It'll shift right toward product to make more. Alrighty, so let's go ahead and finish the problem. Let's calculate the non-standard delta free energy. Oh boy, only one more slide. Okay, so we're just going to plug everything in. We know the standard value of delta G. That's what we calculated a few slides ago. So we're just going to plug everything in now. Well, I guess you can, I'm just going to do it again here. It makes it easier to see, I think. So minus 141.6 kilojoules. Pay attention to units, okay? Plus 8.314. That's in terms of joules, okay? So we've got to divide that by 1,000 to get it to match these kilojoules. Temperature has to be in Kelvin. And then log of Q. We found Q up here. So we're going to squeeze in log of 4. Go ahead and punch all that in your calculator, okay, just to get used to how to enter everything correctly. What you should then get is the non-standard delta G is minus 138. Still quite a spontaneous reaction. Not quite as spontaneous as under standard conditions, but I want to emphasize a point here, and that is non-standard delta G should never be too far away from the standard value, because remember I said all of this to the right is kind of a correction factor for non-standard conditions. So it usually will be pretty close. Alrighty, so wrapping up this PowerPoint is here's a problem, very similar problem for you to practice on your own. So if you are listening to this pre-recorded lecture and you did not attend my live lecture, then you want to make sure you go to Go Formative and answer these questions. That's it.